Good morning, everybody, and thank you for coming to reInvent, first of all, and to this talk about the Amazon EC2 container service. If anyone has been having the kind of show I've had, I'm surprised anyone has their voice left. I'm still trying to figure that one out. What the goal of this talk, so my name is Deepak. I run the EC2 container service team, and what I'll try and do today is talk to you a little bit about why we built ECS, some of the design decisions we took, and sort of the kinds of applications our customers are writing that drove those decisions. And I'll try and leave about 5 minutes at the end. So this room is too big for general Q&A. But there's members from the ECS team here. Please come forward, and we can, if you have any questions, we'd be happy to answer them. So for about 30 years, 40 years, the core primitive of computing has been a server. This could be a physical server, a virtual machine, but the general idea is that you have a set of CPUs, memory, a full operating system. You log into a server to debug it. You interact with it in a generally interactive way, and that's been the case for a very long, long time. If your applications got bigger, you went and got a bigger server. And if your application got even bigger, you got an even bigger server. But at some point of time, that starts to break down. Usually happens when the amount of memory you need on that machine, you can't buy one more than that. Even though today you heard Werner's announcement about the X1 instance with 2 terabytes of memory back when I actually did a lot of computing. It was tough to find something that big. Or the parts got prohibitively expensive because they were boutique parts. So what a lot of folks started doing, and I come from the HPC world, where we started building these Beowulf clusters. For years, we had used these big, large shared memory machines, which were getting more and more expensive and difficult to manage. So what people started doing was getting commodity machines, standard servers, connecting them together, and trying to present them as a single machine. And the kinds of applications that people wrote on these machines were more distributed. So they scaled by adding more hosts to the system, as opposed to going and buying the next biggest system you could buy. So into this world, just over 9 years ago, came Amazon EC2. I remember being insanely excited at the time, probably sitting on a couch somewhere. I did not work at Amazon. And the EC2 announcement comes out. And the reason I was insanely excited was this. The server that the kinds of servers that we used every day at work, the kind of cluster that I'd sat in the computer room next to me, was all accessible via simple API. I could do an EC2 run instances call, and I could get an instance. And by the way, if I really wanted lots of machines, the same run instances call could give me a lot of machines. As the cloud evolved and as we added more capabilities, you could start putting things inside auto-scaling groups where the scaling events would happen more automatically, and I didn't have to go in and type a command every time. And this paradigm, so horizontal scaling wasn't something that EC2 introduced, but it made it ridiculously easy, and over the last several years, it's become the dominant model, the way people run their compute. It wasn't always the case, and in many cases, sometimes it still isn't. But by and large, that's what we see our customers doing. In this world, your applications were still relatively monolithic. But what I mean by monolithic application is that all your components are usually in one WAR file or a single Rails file tree. And the way you used to scale them, many people still scale them, is by taking each application and running a lot of EC2 instances, where each instance is running one copy of that application. You can scale this manually, or more commonly, the term that we use inside Amazon is reactive autoscaling, where you're using some kind of metric in CloudWatch on load or something like that to trigger a scaling action, add more servers. When the load goes down, you reduce it. So simplifying the situation a little bit, but by and large, that's what we've seen, and that's what a lot of applications still function as. But there are challenges with this model. And the challenges with this model are that you have many, many components. Sometimes you want to change one component, but you can't because you can't deploy it because it has a dependency on another one, or a team is blocked because some other component is running far behind, they haven't completed the work. And to update your part of the system, you have to wait for that component to get developed and deployed as well. So what we started seeing, and I suspect many of you here already work in that mode, is people started splitting these components up into their own little services, hence the microservice word, And the idea was that you could develop each of these independently. You could use whatever language you want. You could have a small team. We call them 1 and 2 pizza teams inside Amazon. And you could use whatever way you wanted to develop it, deploy it, and expose things via APIs in such a way that as the new component came up, you could collect it. And you could scale them by using, you could scale them independently of each other. So your order UI could scale on its own set of EC2 instances, and your user service, for example, which has seemingly more scaling requirements, would scale would scale more your user service on a different set of instances. Well and good, but there are some challenges with this. You're still taking a component that you've probably decomposed, and you're deploying it on the same kinds of machines that you had earlier. So you're still thinking in terms of machines. Instances in our case. So what can we do? So into this world came containers. Containers have been around for a very long time. They've been around in BSD. They've been around in Solaris, and about a decade in Linux. Why are containers interesting? Well, containers give you a way to manage your resources, and here your resources are CPU and memory, to pick two. And they also allow you to isolate components a little bit from each other. So containers are operating system level virtualization. They take advantage of kernel features like C groups and namespaces to basically provide sandboxes for your applications to run. And because they're lightweight, they share an OS and kernel, they're really, really fast. Cool. That's been happening for a long time, but until little over 2 years ago, nobody ever came to us and asked us to build a Linux kernel container as a service, even though they've been around for a long time. And into this world dropped Docker. And this was about 2.5 years ago, I think March 2013. And what did Docker get right, that made it so popular? I've heard that the Docker booth at this conference requires some arm wrestling just to get in and talk to folks. They have a cute logo. That helped. If any of you have children, and you show them the little blue whale, they'll love it. Just pro tip. What Docker allowed you to do was take this application and all its dependencies and package it. It gave you a declarative model to take whatever app you had, what requirements it had, and package them up. Probably speaking to the choir here, but just in case you haven't heard about Docker. You could ship it. You could move it from one place to another. It's kind of remarkable that you can take this package, run it on your laptop, ship it to a registry somewhere, and pull it down and run it in production. And that's the third component. It gave you a really lightweight runtime to run this blob. And for the most part, keep the blob consistent across machines, environments, people. And I think around this time, it matched really well with how people had started thinking about running their applications. I talked to you a little bit about microservices earlier. There's many, many examples of companies well before the Docker era on AWS running these very, very decomposed applications. All you have to do is go attend a Netflix talk, and you'll get some good idea of how people do that. But I think you should take this one step further, or at least think about it slightly differently. When we are building and running these applications, what do we need? We've been talking about servers and applications, but I think we need a different primitive. And here's how to think about it. You have a server, an EC2 instance, with many processes running on it. Each of these could be a microservice or your tiny application. But what you really want to think about is not about the server itself, but about this little, we'll call it a task or a job. I like task. And that's the word we use in the ECS world. And basically what this task does is a task can be made up of one or more containers. You can describe it using some kind of declarative syntax. And then what you work with for the rest of your application's lifecycle is that task. You want to think about your app, how you work in this world at the level of this core primitive that you can deploy, that you can move around. And suddenly, you're not thinking about individual machines anymore. What you're thinking about is a pool of resources made up of, in this case, EC2 instances. And what you're trying to figure out is, into this pool, where can I take my task and drop it in so that it'll run appropriately? And since we can call it a cluster. I'm an old HPC hack, so I'll keep calling things clusters, and for the rest of the talk, that's what it'll be. But well and good, you have a cluster. You have tasks that you want to run on this cluster. You need to manage it. You need to understand it and you need to take action based on what's happening. And the analogy I like to use is that of an airplane control tower. I think of the airplane control tower as the leader. Some people in the cluster world will call it, like in the Hadoop world, you call it a master node or something like that. The leader is someone who has visibility into the system, that is responsible for taking actions, that is responsible for figuring out what happens next. And how can they do that? In the aircraft analogy, the control tower knows where all the planes are. It has, through GPS, it has a state of the system. And the system could be planes that are about to crash into each other, and hopefully their job is to avoid doing it. But based on what's taken off, what's flying where, which part of the sky things are in, using radar and GPS, your control tower is making the next decision. Which runway should people land on? Oh, the wind changed, they need to come in from a different direction. They're responsible for scheduling these objects, in this case, airplanes, and in our world, tasks are essentially your planes are your tasks, and your control tower is essentially the leader or master of the service. Scheduling is nothing new. HPC schedulers, there's a great paper that I encourage that people read that describes the kinds of schedulers and the kinds of scheduling systems people should build. HPC schedulers are monolithic. The logic, most of them anyway, the logic of how the scheduling should be done, which is the business logic, which defines, hey, here's where the next job comes, which is more important, so put it there first. And the state of the system and how it manages the state of that cluster are all inside one code base. So that's how everything is managed, because this is one shared system that's used by a bunch of applications, but there's a pretty simple rules around how jobs come in and how they move out. More recently, over the last several years, you have much more sophisticated systems and how cluster state is managed and how scheduling is done. They're effectively two-level systems. What does this mean? It means that you have a leader, your scheduler, the thing that's making decisions, but the state of the system is somewhat separated. They're not one code base. So your leader is able to take action based on some good visibility into the system. And by the way, you can have multiple schedulers coming in at the same time and trying to compete with each other for resources, and you're trying to make decisions like that. There are two approaches. You can do things pessimistically, which means that one scheduler gets part of the view of the system, and while that's happening, it's all locked off, and the other one is getting a view of another part of the system and doesn't have a full view of your entire state. The equivalent would be a control tower that can see the airspace over Nevada, which is where we are, or California, or something like that. The other option is shared state systems that use optimistic concurrency. Here, every scheduler has complete view into the full state of the system. So you know exactly what's happening. All the schedulers are getting the same information, and you're reconciling conflicts at the level of the scheduler. So these are the, as we started this process, this was the technology that was out there. This is what we knew, and that's what we started talking to our customers about. And the first thing, I think it's about little over 2 years ago when we started having people coming to us and asking us for, hey, can you build a service around Docker? And the first question we asked ourselves was, Docker runs just fine on EC2. Docker run is, it's no different from running it anywhere else. Why the interest? And I started probing. It became pretty clear. What people were doing was rewriting applications or writing new applications. These were usually microservices types of applications, or at least more decomposed. And they wanted to distribute these applications on a cluster and wanted a system that managed the lifecycle of these applications. So essentially, it took these tasks that they were running and managed the lifecycle. The couple of other things that they wanted. Number one, they wanted really tight integration in with other AWS services. That's fine and expected. Things like IAM, ELB, CloudTrail for logging, and so on. They also wanted to run multiple schedulers at a time and be able to make prioritization decisions where job one came from one team that was higher priority, job two came from another team that may be lower priority or a batch job of some kind, and job one always won in those kinds of situations. So it became pretty clear to us that we wanted to build and needed to build a shared state optimistic concurrency system, and that's exactly what we did. This is a high-level block diagram of ECS. Various components, and I'll try and, over the next few minutes, go over some of these components, what they do, and kind of how the system works and why we made some of the decisions, and kind of how you can use it and how you can think about using ECS. The first thing you do when you use ECS is launch a cluster. And the way you launch a cluster is just an object. It can be empty. It's just a name. Into this cluster, you launch one or more Amazon EC2 instances. We call them container instances. And the only requirement for a container instance is, one, it should be running a modern version of Linux on which you can run Docker. And it needs to be running the Amazon ECS agent. You can launch these instances in one availability zones, multiple or 2 or 3 clusters in ECS are regional. They're also heterogeneous. You don't have to launch one instance type. You can launch a mix of instances based on your requirements. Auto-scaling does require you to put instances in homogeneous mixes, so you can have multiple auto-scaling groups in a cluster, for example. The Amazon ECS agent is what basically, if you can read the GitHub page here, it's basically what takes and sends commands from ECS to Docker and does authentication, tells the ECS service that this container instance is now part of this cluster. It's registered in the service, and you can start doing work with it. The agent is open source. It's written in Go. It's on GitHub. And we love getting pull requests. So if you use ECS and you have some features that you'd wish the agent had, let us know. We are happy to take a look at it and see if we can add it in. The agent itself, at least with the Amazon ECS optimized Amazon Linux Army, runs inside a Docker container. So that's how we tend to run it. But you can put it into an RPM, make it part of the system. We give you an init. There's also a sister init component that you can get, also open source. And once all of this is done, then the ECS service takes over. And the ECS service itself consists of roughly 4 components. There's an agent communication service. This is what's responsible for communicating with the agent and does the two-way communication. You also have the APIs. I'll get to those in a minute. But the heart and core of ECS is your cluster management engine, which is responsible for managing the cluster, for maintaining its lifecycle. That's built on top of a key value store, which is the heart of the ECS system. So the key value store that ECS is built on is a core distributed systems primitive that we've built at AWS over the years. It's used at many places inside Amazon. But what it is essentially a highly available and highly scalable Paxos-based transaction journal. So you maintain it has a history of state transitions that it captures over time. And these transitions are offered and accepted using optimistic concurrency. So it's an OCC system. And these accepted offers are then replicated along this. And then you can make all kinds of decisions because you know that this is consistent. You know what, when you ask the journal for a piece in the transition history, you will know exactly which transition you're looking at, and then you can make decisions based on it. So on top of all this system sit the ECS APIs. These APIs, and the ones you should care about right now, are these. We call these our read APIs. You can list and describe the 3 core components that make up the ECS system. Clusters, everything in ECS happens in the context of a cluster. So by default, everyone gets a default cluster, but you can give it another name. But once you have a cluster running, any future command happens in the context of that cluster, and you have to specify it unless it's default. And you can describe and list and describe clusters. You can list and describe container instances. These are the hosts on which your containers are going to run, and you can list and describe the actual tasks themselves. With this, these APIs together give you the state of the system, which is why we call them our read APIs. And once you know the state of the system, then you can decide what to do with your next task. And that's where the start and stop task APIs come in. The start task API basically says, take this task and run it on this container instance, and you make that decision based on which container instance may be the one you want to run this task on. And this has allowed us to build a really nice, really scalable system. And as we talk to our customers, it is this backend scalability and robustness is what they like about us, about ECS, as much as anything else. So let me share some more specific data. In this chart, you are seeing 2 clusters. One is 100 nodes, so 100 container instances. The other one is 1,000 nodes, so 1,000 container instances. The numbers you are seeing in the rows are your, so the rows are the 50th, 90th, and 99th percentile latencies, end-to-end. So when you have a client, you submit a request, it takes the task, launches it somewhere, the Docker daemon starts the task, all the containers, and you send an ACK back to the client, and the client says, OK, now I can start, now it's running. This end-to-end latency, and the columns are how well utilized your cluster is. 10%, 25%, 50%, 90%. 90% is like a pathological case, because most people will auto-scale before they hit that. And as you can see, almost independent of cluster size and cluster utilization, your end-to-end latencies, so this is client and server, are 1.5 seconds at the 50th percentile and less than 2 seconds at the 99th percentile. So these are your outliers. So that's well and great. What if we could go bigger? This is a 3-day load experiment that we ran. You're starting with something like less than 1,000 instances and going to over 8,000 instances. That big purple squiggly line that you see is the same time frame. So you're starting off with a smaller number of instances and going much larger. That count is the count on the y-axis on the right, which is the request rate in 5-minute intervals. And what you see is that your API response latencies at the 50th percentile and the 99th percentile, stay low, less than 100 milliseconds for 99th, and I think about 25 milliseconds or so for the 50th. And they're essentially independent of cluster size, and they stay flat, and they barely move. So most of the effort that we've spent, especially in the early days of ECS, was building out this very robust system that you could pretty much throw anything at, and it would be able to take very large clusters, multiple zones by default, and you don't have to think about how you scale your state management system or your cluster management system as your system grows. It's the same API calls, where they're running one node or 8,000, where they're running one task or 80,000. I think that's around what we were running there, or things like that. So you can throw a lot of load at it. So far, we've talked about taking an individual task and manually, well, using the API, running it on a particular instance. But earlier, we were talking all about scheduling, and when you're running 8,000 nodes and many, many thousand tasks, you don't want to actually do it by hand all the time and try and figure it out. And the way we built the system was the scheduling layer for ECS actually sits on top of the ECS APIs. And here's an example of where you can write your own scheduler. This is a blog post that we published maybe a couple of weeks ago that gives you a simple example of what is called least task scheduler. It takes a look at the system. It measures the state using a list and describe APIs, and then based on that, finds the instance that's running the least number of tasks and launches the next task on it. It's very simple. It also links to a little Go library that you can use that maintains sort of local state and helps you write good, write a scheduler yourself. And you can write any kind of logic. We have a number of customers, including some who have spoken at reInvent, who've written their own schedulers based on their specific requirements. The other fun part about this is, let's say you've been using some other scheduler and you've been using some other kind of system. You can, in theory, write a little piece of code, a little shim, that converts the state response that scheduler is expecting, and take the ECS state and convert it into that. So let's say you're using a scheduler for a system like Mesos. So we've done just an experiment where we wrote a scheduler driver that you can use Marathon on top of ECS, and Marathon just runs because they're converting the ECS state response into a Mesos offer. That's a good example. That's one example of how you can use it. But most people actually don't want to spend time writing their own schedulers, and they don't want to have to write shims. They just want to write they just want us to provide a scheduler for them. And for long-running applications, we have what's called the ECS Service scheduler. ECS has two schedulers, what we call run task, which is just a random run once. It launches the task. If the task dies, it goes away. It doesn't try and do anything smart. If it finishes, it finishes. The service scheduler tries to do a lot more. It's designed for long-running applications. I thought of doing a demo, but because this was going to get streamed live and I didn't want to do any crazy things, you'll get a demo of screenshots. So the first thing you do is you create a service. Hopefully you can read this, but essentially what create service does is you define you point to the task definition, which is essentially your declarative application. You tell it what cluster it needs to be in. You give your service a name, and then you you basically say, I want one copy of this running. You can optionally put it behind a load balancer and then give a service role if you're using an ELB or some other AWS component. These services launch tasks and they manage tasks. Your task definition, it's JSON, but you can also build it using the ECS console. This is a very simple task definition. It has 2 containers. These are standard Docker kind of features. You give it an image name. You tell it how much CPU it needs. You tell it how much memory it needs, what ports you might want to expose, what Docker links you might have, and whether it needs, and any other additional commands that you might have as well. And at the end of it, you have essentially a desired state of the system. In this case, the desired state is very simple. I need to run one copy of that task, and I want to keep it running. And what the system basically tries to do is keep that one copy running. In the screenshot you're seeing, it's launched one task. That task has gone from desired, and you have one running count, which means the system has stabilized, and it'll try and keep that state going. So if you point to the ELB, you get this really simple application. You can probably do fancier stuff. But you have a running ECS sample app. And I think we have the sample app in our console or something like that, or somewhere, which you can get your hands on. What do you do next? You may have a scaling event where you want to run more copies of your tasks. You want to run, because you're taking more traffic, you have a 3-node cluster underneath. So you might want to scale to 3 tasks. And you update your service. And what you see here is that one task is already running. That's the one I already had. And you have 2 pending tasks that are waiting for the system to get it running. And at some point, very soon, quickly, they'll all be, the system will converge to a steady state. Everything will be checked in behind the load balancer, and you can take traffic on all your 3 hosts. ECS also exposes an event stream, a set of events on what are the transitions that are happening. In this case, what you see is, hey, you had 2 new tasks that checked into a load balancer, and then they've started taking traffic, essentially. You may also want to automate your fleet. I have a 3-node cluster here. You may start taking enough traffic that 3 nodes are not enough and you need more. About a month or 2 ago, we started publishing 1-minute metrics to CloudWatch for clusters and services. So these are aggregate metrics. They give you CPU utilization and memory utilization across your entire cluster or across the service or the services that you're running on that cluster. And you can use those metrics to scale the fleet that your tasks are running on, that you can automate things. You may also want to update your application. So you have multiple components. This is one of those applications where different components are being developed by different teams. One of these teams has a new package. Task definitions in ECS are immutable. So once you launch a task, if you make any changes to it, it gets versioned into the next one. So if you want to launch an update, you can choose the new version and say, I want to update that. And essentially, we have the concept of a deployment where you're going from one version of that task to the next version. What does this mean? You have to drain connections from the tasks that are already running. You need to shut down those tasks, launch the new ones, and then reconnect them to an ELB. And the system does all of this for you. You don't have to do that. And so, you had this application running, you updated it, and now you're running a new application, which it's very complex, and I worked very hard at it, but it kind of works. All right. Sorry, it's dry in here. There is a third component to running distributed applications on a cluster, and this is much more prevalent in a microservices world than in your old school sort of HPC kind of world that we talk about, and that's service discovery. And my best analogy for service discovery in this aircraft control tower example that I use is, just imagine there were no human beings in that, and you just had machines making the decisions. Everything was happening automatically. We lived in some future world where people no longer sit in control towers. Here, as another one plane takes off, another one joins it, each plane is always aware of each other. They're discovering each other, especially those that need to be aware because they're going to the same airport, and they both can't land on the same strip at the same time. And so these are the kinds of decisions. Today, a human being is saying, OK, you come on this airport, you hang around a while because the president is landing or something like that. And the services discover each other automatically, and it's very dynamic as services come and go, which is the kind of world we live in today. There are 3 ways to do service discovery with Amazon ECS. The first one is using the ELB. All your services are running behind a load balancer. You can use that load balancer and the ECS APIs to find where each service is running. That's simple, not too complicated. It's a kind of model for service discovery that's been around for a very, very long time. The other one, and we have a blog post that shows you how to do it with Console, is to use a system like Console or etcd. These are configuration management systems that you can store your configuration in there and use those for discovering other services that your tasks need. It's a little more work than the ELB example, but it works pretty nicely. And another great example, and they just published a blog post today, well after I had to lock my slides down, so you should go check that out as well. But the folks at Weave have done a really, really good job of integrating Weave with ECS. So you can manage networking on ECS using Weave, you can do service discovery using Weave, and you can then visualize those services and applications using Scope, which is a visualization system. And it's a great partnership, and you'll probably see them doing even more with that. And there'll be other examples of other partners who will do something similar. So that's awesome. You have running clusters. You have a system to schedule tasks on those clusters, and you have a way for new services to discover each other dynamically and maybe even use that service discovery mechanism to trigger new actions. So how are people using this in the real world? If you've been around the conference, I actually forget what the order of these talks were. You've already seen a number of talks from our customers using ECS. In Werner's keynote today, you heard from Remind. Jason talked a lot about why Remind chose ECS, what they're trying to achieve with it. One of the core things they had was every August their traffic goes up. In that talk, he also mentioned some of the advantages of failure modes and robustness. And this graph, which is in a blog post that the folks at Remind wrote when they open sourced Empire, gives you a good idea of why they chose ECS. So the lines at the left are their latencies at various distributions, average 95th and 99th. And then vertical line is when they switched over. And not only did their 99th percentile latencies, all of them, but especially the 99th, go all the way down, they stay very stable as well. And this is the big reason why they run on us, because they don't have to worry about scaling the system. It just does. Another great example, and one I'd definitely encourage people to look at, is Khanbox. Khanbox was developed by a bunch of folks who really like building great user experiences. Noah, who's the co-founder of Khanbox, one of the things he said is that he's managed a bunch of orchestration services all over the place. And he's done, one of the things what they liked about ECS was two things. One was they didn't have to worry about the backend scaling, leader election, all the complexity that you need in a large distributed system. And they also got the opportunity to take advantage of other AWS services out of the box. And that works really well. And this is just a screenshot of the Khanbox CLI. It's pretty neat, pretty easy. And if you use Docker and you want to run apps, 12-factor apps or so using Docker, this is a great system, as is Empire, which is what Remind have developed. Another third example is Meteor. I'm not a JavaScript person, so I'm not super familiar with how people use Meteor, but apparently the JavaScript folks like them a lot. Last week, Meteor announced Galaxy, which is their JavaScript application platform. And there were many reasons they chose ECS in the end, but the key reasons were, one, they can run thousands of containers across multiple availability zones without having to worry about the scaling characteristics. And then they can use things like CloudFormation templates. You can automate things really well, and you can integrate with a bunch of other AWS services. The key message across all of these is it really simplifies the overall user experience and allows these overall operational experience for these customers, and allows them to focus on the application management and deployment part, which is what their customers want. All right, well and good. This is kind of the core ECS system. It's been around for a long time, but we want to keep improving the service. And so for the next few minutes, I'll talk about some of the announcements that we made this morning that Werner made and give you a little more detail on them. The first one is the Amazon EC2 Container Registry. Our goal is to have the registry available later this year. You can sign up for early access, and just to let us know that you're interested at that URL below. What is the EC2 Container Registry? So it's a fully managed Docker registry, so it's Docker compatible. It's integrated with Amazon ECS. You can use the registry APIs. You can use the Docker CLI with this. It supports SSL and is encrypted at rest. But I think one of the core features that our customers wanted us to develop was the integration with IAM users and roles. So it's very, very tightly integrated with our identity and access management system. So registries, repositories, images in those, you can have very fine-grained access control. Who can deploy, who can create one, who can download one, who can upload one. It'll be available in multiple regions. Our goal is to have it in every region that ECS is available in. You don't have to use it with ECS. You can use it on its own. And it costs 10 cents a gigabyte a month. If your ECS resources are in the same region as your registry, that's all you pay. If you are downloading it to your laptop or deploying to another region, you pay standard AWS data transfer costs. So that was the main first one and sort of the new big feature that we announced today. The other one is AZ-aware scheduling. AZ-aware scheduling, essentially, right now, well, till yesterday, our scheduler would randomly place new tasks across instances, even if you had instances in multiple availability zones. As of today, what the scheduler does is it will try and make sure that new tasks are launched in such a way that you have balanced tasks across AZs. It does it by default. And the main goal is to improve your availability and get more efficient load balancing. It's a commonly asked for feature, and you can use that right now. The third feature, and maybe I'm super partial to this, is the first version of the AWS CLI. We have a ton of work, we have a ton of ideas on where we want to take this. But the AWS CLI's idea is that you have a much simpler workflow that starts on your laptop and ends on an ECS cluster. So you can do ECS CLI configure to get all your creds and all set up. You can do ECS CLI up to actually launch your cluster. So you don't have to go to the EC2 or AWS CLI to do that. You can launch it from there. And then, for those folks who use Docker Compose, let's say you have a Compose file that you're working with locally, and you've done a Compose up to run it on your laptop. If you do ECS CLI Compose up, you have the same Compose file running on ECS as an application. And I suspect some of you probably went to Jerome's talk yesterday, and he gave you a preview of this particular CLI. The CLI is available today. It's also open source. Since it's very young, I suspect there may be many features that people want. And again, we welcome pull requests, so please do. I'm sure the team will be super happy to get them as well. And the last feature I wanted to talk about was improved Docker container configuration options. So when we launched ECS, our agent modeled just a subset of the Docker functionality because that was robust. We wanted to keep it light. But we started hearing from some customers that they wanted to do more and more. So the things that we've added a much more, a larger set of Docker features and updated our console to be able to support them as well. And these are things like host names, Docker labels, working directories, privileged execution, which is the most commonly asked for one because everybody wants to run Docker in Docker, and things like log configuration and more. There's too many to mention here. You can take a look at our documentation. So essentially, what we've tried to do over the last many months is build a system that's designed to run container-enabled applications in production, especially if you're someone who's running multiple applications on one cluster or on multiple clusters that wants to take advantage of things like IAM and the scalability of our system and essentially move really fast without worrying about the muck of scaling and identity and some of the things that AWS brings you for our other services. And ECS is well designed for that. And if you are running a small app or a large app, we'd love to talk to you about how you're using it. So with that, please remember to complete your evaluations. And thank you very much.